My name is Keith Clarke. I started out as an electronic design engineer back in the mid-80s. I did my degree, and by 1989-90 I was working for an aerospace company, and I built my first silicon chip that was destined for the Typhoon fighter aircraft. I was building some functionality to control a display on the design. Then fast forward a few years, I joined Arm back in 1993. It was Advanced Risk Machines. Back then, there was fewer than 40 people in the company, and my role was to build one of the first SoCs based around an Arm processor, the ARM-7500. Myself and two other engineers put that together over a course of about 9 to 10 months, pulling together existing blocks into a single chip Acorn computers would subsequently use in a computer. And then I moved on to a project to port the thumb instruction set into the ARM7TDMI processor, so the first ever reduced code size instruction set in the ARM processor. I did the first logic design to make that be so back in 1995. After that, I worked on many SoCs with customers, helping them put together Arm-based designs all the way up to year 2000 when I started leading the CPU design team here in Cambridge, and then had a subsequent career of engineer manager, program manager, technical marketing, a range of different roles right the way through. In 1990, the first chip I was working on was for an aerospace project, and it's actually for European fighter aircraft, and it was an ASIC with about 75,000 gates or 300,000 transistors. So that was my first project ever, and I was really lucky to be on this. It was quite advanced at the time, using the latest technology, using the latest tools to develop it. We were even using a design language to design the logic rather than individual gates. So it was really high-tech stuff at the time. As an individual engineer, you're only going to be working on one part of a big system. When I was working on this device in 1990, the chip was one part of a very large system that included multiple chips and multiple systems to produce an image on a display that a fighter pilot could read at a glance. I was just working on one or two functions within that chip, within a much larger system. I didn't have to know everything about the whole system, but I did need to understand enough about how my part interfaced to the parts around it. And the same is true now. If you're working on a very modern SoC that has billions of transistors, you'll be working on one part within that interfaces to other devices around it that happen to be on the same chip rather than different chips that they were when I first started in the industry. So it's a similar concept. You have to know what you're building, know how it interfaces, and it's useful to know the bigger picture enough to know where it's going, but you don't have to understand everything. So there's nothing to fear in that sense. It's been really important over the years to help accelerate SoC design around ARM processors and in general. Actually, the very first ARM processors, and going back to what I was saying earlier about as an engineer on a project building a very large chip, you're concerned about your block and how it interfaces to the AMBER interface. Yes, you do need to know a bit about what you're interfacing to beyond that, but the way in which it talks to the bus is standardized. There's test benches to test it, there's a standard to follow, and it just simplifies building the device and simplifies your life as an engineer. Well, software is nowadays a very large part of the overall development of any kind of complex system. And so if you choose the right hardware IP, then there'll be a lot of software already available, a lot of libraries, a lot of highly verified code out there that you know the hardware IP is already going to work with. And there could be 10, 20 times as many software engineers as there are people designing the chips. It may be even more depending on the development. So it's extremely important that the hardware you choose, the IP you choose, already has a very large ecosystem of very stable, very well validated software and optimized for that purpose. So I can't emphasize enough how important that is, just because of the scale of the software challenge nowadays. How does the concept of logic reuse scale from the classroom to the industry where you have very large developments? Well, I think the fundamental concept is the same, where if you are to build any device of any complexity, then there's probably too much design for the number of people you have to design it. So you are unlikely to build any new device from scratch, not using any previously designed logic. You're almost certainly going to pull an existing design somewhere along the path. And so whether that's in a classroom project, a lab, or in industry, you're almost certainly picking up something that's already been built partially or fully, and you adding things around it or configuring it. So I think it scales very well indeed. And you can just do more if you pick up something existing. For example, take an existing device and build some peripherals around it, or configure it in a different way and measure how the processor, for example, works in different ways depending on how you've configured it. So IP reuse is something that we at Arm, obviously that's why the company was formed, the reusing the processor IP, the fundamental reason why Arm was founded in the first place. But what we found was, when we started developing peripheral IP, was how much effort it took to go from something you've developed to use yourself to something that other people could use. That gap between I'm going to reuse it personally and someone else reusing it was quite large. And if that someone else is your work colleague 2 or 3 terminals down, you can have lots of face-to-face meetings and you can explain it, and they might be able to reuse your block. If that person is on the other side of the world and has no access to you personally and has just bought the IP, then there's a lot more work you need to do to make that IP usable by someone else at a distance. And that's how the whole IP reuse concept comes in. We used to guesstimate somewhere between 3 and 6 times the amount of effort to turn something from a nice piece of functionality to something that could be sold as reusable IP. And let me give you an example. We started working with a large telecoms company who had a Bluetooth block in the days when Bluetooth was a very new function. And they said to us, "Hey Arm, you're good at producing IP. We have this Bluetooth piece of IP. We'd like to sell it to other people. Can you work with us to turn it into IP?" And we did. We went and visited them in Scandinavia. And we realized as we went through it, they had no concept of how much extra work it would be to take their block they'd built for themselves and turn it into IP that other people could use. But we, because we had the experience, were able to work for all of that, and we were eventually able to license this core to other people. But it was hugely important because not everybody was able to build their own Bluetooth IP. It was a very new and difficult standard initially. And they were able to say, here's the hardware and the software to go with it. And it was transformational for companies to be able to pull that block in and have a Bluetooth interface on their device in the days when this was difficult new technology. And I think it's a really nice example of IP reuse. Not everyone's going to build their own Bluetooth device and all the software to go with it. So might as well buy it from the experts who know how to do it. But the IP packaging and the reuse was the key piece there. And you want to be buying IP from a company that really knows how to package IP so it just works when you plug it into your device. So because our whole business was dependent on us selling IP to other companies, we had direct experience of what it took. When you actually delivered the IP, the companies would come back immediately and say, oh, we need a view that looks like this as well, please. And we need the documentation that tells us this as well, please. And initially, of course, we said, oh, what do you need that for? And they'd explain, and we would say, oh, we need it because we have an engineer that's doing this job and it's important. Oh, yes, of course. So we learned it's a classic case of learning curve. We Arm, the IP company, our learning curve meant that we were so far ahead of companies whose business was selling chips or selling systems. They just hadn't got the experience of doing this. Even if they were reusing a block within their own company, they could still rely on an engineer to engineer having a coffee meeting together or sitting together to solve problems. We couldn't depend on that, and so we had to make everything clean and easy to use. And so our learning curve, and everybody in the company having the same mindset, we're here to build IP, we're here to sell that IP many times over, meant that we just learned how to do that much more effectively and efficiently. So what's the difference between full custom and semi-custom VLSI design, and what does Arm provide or use? So if I go back to the very beginning, the first Arm processor designed in 1985, technically I'd say was actually semi-custom, because they built what's called the data path, the piece that does the calculations, adds and maths, if you like. The data path was built out of specific transistors and a very specific layout, and was literally drawn on a computer to work in a certain way. The control logic around it, most of that was built out of little building blocks called logic gates, and the designers would pick those logic gates to make the logic function they need, and then engineers would lay those out on the screen and connect them together. So that element was semi-custom. Not every single transistor was redesigned every time, but as a whole, the device you would look at and say, oh, that's a full custom block, because it was delivered and sold to our customers when Arm was founded as a box, if you like, a black box with connections around it. So as far as the customer's concerned, they were picking up a full custom chip that they could drop into their design. So in a sense, Arm was more full custom in those days, but there was actually a little bit of semi-custom under the hood. As we evolved, we gradually introduced more and more semi-custom, in the sense of using logic blocks that were already pre-made. The most obvious one is memory. So if you wanted to build some SRAM on a chip for CPU cache, for example, you didn't design that from scratch every time. You had a set of techniques to produce it from automated means, and that's a kind of semi-custom design methodology to produce the memory. Over time, we moved from this full custom with a little bit of semi-custom under the hood to more and more reuse, in the sense of we were using Verilog, or initially in fact some VHDL as well, to write the logic and then synthesize that to gates, and then use an automatic layout program to lay all those gates out. So over time, we moved to a state where all of the control logic was synthesized from Verilog. The data path was still being built manually, or mostly manually. But then we evolved over the period from about 1997 through to as late as 2004, our processors were becoming more and more synthesized from these high-level languages, to the point where from 2005 onwards, all of our processors were always built using this synthesized method. So that is a semi-custom method, if you like, in that we delivered the high-level Verilog, and that was translated down into gates, and then those gates were laid out to produce the block. SRAMs were attached to that, and you could build a CPU like that. And we gave our customers the ability to do that themselves, and so they could fit it into their SoC more easily. So we transitioned to a semi-custom approach that our customers could use as well. However, initially, interestingly, quite a few of our customers said, "Oh, actually, can you just provide the hardened CPU core for us, even though it's synthesized and place and routed? Can you do that for us?" So we had a service team that did that for some customers. So they still found it easier to pick the CPU up as a hardened block, and then they could do the rest of their SoC design around that. Nowadays, other companies may provide that service, or there's tools that can do it, but it was an interesting transitional phase. So how is software used to validate and verify IP designs? That's a good question, because it can be used all the way through the design process. And if I go back and give you some examples, when I first arrived at Arm, we were using a simulation tool that allowed us to write logic in a particular way, and we could check whether our design worked by running code on this Arm CPU that was part of the little system we were designing that would check the functionality was as we expected. So actually, the very first designs I did, I was using software to test the functionality, but I was actually writing very, very low-level Arm instructions, one after the other, to test the IP. So that was way back at the beginning. Since then, we've evolved into a much more mixed approach within Arm, and would be the case within any development, whether you're in a classroom or on a bigger development. You would tend to build your piece of functionality and build a test bench around that to test that function on its own as well as you can before you move out to the next level. And it might be 1, 2, 3, 4 steps before you're at the system level, where you can start running code on a processor that tests your function. So it depends where you are in that flow. But within Arm, we would have, say, a test bench at the block level. We might connect several blocks together and have a test bench that tested those blocks together. You're still not running software at this point. It's very bespoke to those blocks. But then eventually, you're running an Arm CPU level, and then you'll be running a lot of instructions to test that the CPU is functioning exactly as we want it to. And we're not talking about hundreds of thousands of instructions or even millions of instructions. We're talking about billions and billions and billions of instructions of different types, many times randomized, to test that the whole function of the CPU is correct still. And down within that CPU, there might be your little block. It's a state machine or a counter or some complex piece of logic that is being tested in that process. Now, if we scale out to somebody build an SoC, a similar thing, back to my earlier example, you may build a test bench for your block, but then you plug it into the SoC and then start running software to check that the function as a whole is doing what you want to. So software is extremely important in verifying the functionality of an SoC, but you may start at a level below that to give yourself confidence before you connect it in and start doing the next steps. So what are the advantages of using open source IP versus licensed and proprietary IP? Using open source IP, you're reliant on the community around that open source device in order to do the verification for you. And it depends on how big a community there is for how good a job they're going to do with that verification. It may be quite good, it may be substantial, it may be still its early days and there's more work to be done. The question I would always ask is, who's on the hook when something goes wrong? So when you're buying from a company, if something goes wrong, you contact that company and say, help me fix it, give me a fix, and their job is to fix it as quickly as possible for you because they've sold it to you and they want to ensure that you get a good experience. If you download from an open source community, something goes wrong, you then put a post saying, oh, can somebody help me with this problem? You may or may not get a response. You may get a response in 24 hours, or you might get a response in 2 weeks' time. You just don't know. So there's a definite difference in potential service. But there are, to be honest, there are examples of companies that sell open source bundles of software, for example. So Red Hat are famous for selling server software bundles, and they do a lot of verification work so that they're confident this particular version works on this server. And if something goes wrong, you call up Red Hat, you've paid them money, and they will sort it for you. And that's true in the hardware IP industry as well. And there's the other element, of course, which is a company like Arm selling their IP. The quality of that IP is their business. It is the thing that they care about almost more than anything else. And if anything goes wrong, then they are genuinely mortified and want to fix it as quickly as they possibly can, want to understand the problem in depth and make sure, if at all possible, it doesn't happen again. And so there's a learning curve as well. I mentioned this earlier. Arm learned how to verify IP, how to verify CPUs, how to react to issues, how to quickly solve problems and try and ensure it doesn't happen again. And that learning curve has been going for 30 odd years. So that's what you're buying into when you're buying from a company that sells your IP, or you're buying into their learning curve and their desire to make sure you have a good experience. So what are the typical milestones and design freeze points in a typical chip design project? I think lots of companies will have their own terminology for doing this. We in Arm came up with some in the early days, which actually I was part of coming up with some of those terminologies, but we realized that it was really important to have milestones that everybody aimed to meet that created a sense of stability from which you could start doing some testing and further processing of the IP. And then you then build towards the next higher quality milestone, and so on and so forth. And the initial one will have many names, but you could call a development milestone, where you just say, I've produced a piece of IP that has most of the functionality, has the connections that would allow it to be connected to other pieces, and you can start to build the whole piece of IP, but it's nowhere near finished. But at least you can start to see the skeleton. It's got most of the logic in there. From that, you can start to run some of the further processes like layout, synthesis and layout and place and route. So that's an early development milestone. And you might have multiple of those. Excuse me. You might have multiple development milestones where you talk about we're going to add functionality X, and then the next one will add functionality Y, and so on and so forth. The first big milestone where all of the functionality, or almost all of the functionality is there, we would call alpha. And so you now have your design with all of the functionality you believe should be there, and you've done some basic testing, but you're nowhere near finished. So that was the very first one. And that can take quite a long time from your start point to get to that point, but it's a really good point. You can start to see how big the device is, how many gates, how fast it is, and it's a really good point at which you can then learn more about the overall device. The next one after that, the big one, is beta, or beta if you're from the other side of the Atlantic. The beta is where you have a lot more confidence that all of the functionality has been tested and seems to be working. So you've run a lot of software. If it's an ARM processor or a system, you've got a lot of confidence it mostly works, or almost always works, but you know there's more testing to be done. And then you enter this final phase between beta and, there'll be many names for it, but let's call it the release for prototype. In that phase, you will then run a lot of additional tests, some of which are highly random and stressing the device from many different ways. And at the end of that, you would say, okay, in simulation or using an emulator, we've got very high confidence that design is now what we want it to be. So much so we're willing to spend the money to have a prototype piece of silicon made. And that's obviously a big step. And it's millions of dollars and a big time to get your first chip back. So you need to have quite high confidence at that point. So that's release for prototype. A few months later, you might get your device back, and then you can start to run even more software and even more tests on it. And in the meantime, you may have been doing more testing in simulation. And then at some point after that, you'll get enough feedback, you'll do a few corrections, and your device will be ready for mass production. So in summary, I'd say it's the development milestones, alpha, where the functionality is there, beta, where you think it's all working, release a prototype where you've got high confidence to spend a lot of money producing a chip, and then at some stage later, you're willing to commit to high volume manufacturing. So what's the smallest and largest SoC that I've worked on, and how do these vary in terms of number of cores and how much RAM? Well, so first of all, I'd admit that my first device I worked on was back in 1990, and the last time I worked personally on chip development was 1999. So I haven't got the most up-to-date information, but I'll start at the beginning. So that first device I was working on, I mentioned earlier, was about 300,000 transistors, 75,000 gates approximately, and there was almost no memory on that device. It was right at the boundary of what was possible. The actual physical silicon would have been about 10 millimeters by 10 millimeters physically, so it was right at the limit of what we could do. It was 1 micron silicon technology. So come forward a little bit to when I joined Arm, we worked on an SoC called Arm-7500, which was being designed for Acorn's computers. So that contained a CPU with 4 kilobytes of cache. So there's a little bit of memory associated with it. We had a video controller that could write out to, could display to LCD monitors or different types of external viewing. We had a memory controller so it could talk to external DRAM. We had I/O control as well. So all of that on one chip was about 800,000 transistors on 0.8 micron technology. So we're now already starting to introduce memory. It was significantly more performance than you could do even 2 years, 3 years before. But nowadays, that would still be seen as a very, very small device. If I come forward a bit more to around 2002-3, somewhere around there, Arm built a device which was an ARM11, which had much bigger cache, perhaps 32 kilobytes of cache, and we built onto that a much bigger system of components, including, forgive me, it may have been slightly later, we also put an early graphics processing unit on that piece of silicon as well. So we built a test silicon that had a processor still with a relatively small cache, an early graphics processing unit. Not even sure we had very much additional memory, quite a few other functional components. And now we're talking about something that was perhaps 4 million transistors. So you can see it's getting bigger and bigger. But even this is nothing compared to the very latest devices. So that was probably the last one I was familiar with. If I go back to Arm-7500, there was 3 of us who were building that. We were using IP components, internal reuse components, but there was 3 of us designing that SoC, putting it together, all of the work to check that all these parts together worked, and taping it out. So it was a completely different level of experience. But that was one of the world's first really usable system on chips. It had a processor that ran at a decent frequency, 30 odd megahertz, it seems nothing now. And Acorn built computers out of that device. You literally attached keyboard, memory, mouse, screen, the interfaces to other devices like floppy disks, and you had a computer, and that was one of the very early SoCs that really said what it was on the tin. But obviously, what you can do now is transformationally more complex and capable than what we were doing then. The question in summary is, about 20 years ago, there was a concern that the number of transistors you could actually use on a device would become quite small because the power consumption of transistors seemed to be going up at an exponential rate, and nobody was sure how you would ever build a device with 9 billion transistors that didn't overheat and evaporate as soon as you turned it on. So what has allowed us to make progress? How is it that we are actually able to use all of the space on these very, very large silicon estates? There's been a lot of progress, and some of the things that were feared back 20 years ago have, fortunately, they found solutions for. So some of that is what's called dynamic power consumption control, and some of it is static power consumption. So simplistically, when you build a stack of transistors to do logic functions, they were traditionally built so that when they were in state 1, they were consuming no power. When they were in state 0, they consumed no power. But as you switch between them, you had to charge or discharge capacitance, and so you were discharging energy at that point. So back before about 130 nanometers technology, most of the power consumption was dynamic power, where transistors, logics switched from one state to another. And so all of your techniques up to that point were in order to reduce the number of switching states happening either simultaneously or within a certain amount of time. So you were controlling how much was switching. And we used a lot of techniques to turn off the clock, for example, to areas we weren't using. Back on 7500, this very early device back in 1995, we wanted it so it could potentially be used for portable devices. So I built a function into it so that when you wrote to a register, the clocks were stopped to a whole area until an interrupt happened that turned this back on, and then the device could continue. So it was an early clock stopping mechanism, and that's been used for many years. And then we would also introduce techniques like dynamic voltage and frequency scaling, because we knew that when you reduce the voltage, the power consumed dynamically is less, but the transistors switch more slowly. So if you're in high performance mode, you would have a higher voltage and a higher frequency, but when you didn't need such high performance, you could wind the frequency and voltage down. And so that was a technique we introduced along with many others in the industry, and that is still used actively. However, the big fear, this dark silicon prediction of 20 years ago, was over the fact that even when you weren't switching states, the transistors were still consuming power, so-called static power consumption. And I won't go into the physics of why. It was partly to do with the voltage reducing, getting closer to the inherent threshold voltage of the transistors, but also because we were making the transistors smaller and smaller and smaller, and the distances were such that electrons were jumping from one place to another when previously they couldn't. So we'd get static leakage. And so now you need to deal with static power consumption as well. And the industry has come up with a whole load of new techniques to do that. So for example, if you change the voltage of the substrate and move that, you can alter the amount of leakage current you get in an area of memory, for example, that you're not using. Or you can actually have a switch, a transistor that controls the power completely to a whole area, just turn the power off. So the whole area has no power, it's zero voltage. So if you know that this area is not being used, you can just turn the power off. Of course, it loses its state potentially, but then there's other techniques you can use. So there's a lot of industry innovation, some of which Arm was proud to be part of, some we did in partnership, lots of other companies coming in with techniques. And an SoC design today will incorporate some or all of these techniques to ensure that as the device is operating, those pieces that are not being used are consuming as little power as possible. those pieces that are being used to perform a function are using no more power than they need to get the job done. And it's a combination of these many different techniques has allowed the industry to continue advancing despite this fear that actually they would just evaporate when you turn them on. But that hasn't happened because of industry innovation, and that will continue. So SoCs are built today out of a lot of IP blocks, often bought from other companies' already existing functions. But companies will also build their own proprietary hardware within that, their own IP. What motivates them to do that? I think the main reason, the good reason, is because they want to build an SoC that fits their particular purpose, and they may have a speciality. So a company that, for example, builds chips that network via Wi-Fi, for example, they may be the specialist in the radio interface, and therefore that's where they're building their own proprietary hardware. But they're not specialists in building a CPU, so you might as well buy that CPU as an IP, plug it in next to your proprietary hardware. Or perhaps you're building the next generation AI chip. Again, you might have some special knowledge, and that's your industry competitive advantage. So you're going to build the piece that you have the expertise in, that you have the engineers to do, but you're going to buy the IP for everything else because it's going to be a much faster design. If you mix those two elements, you're going to spend a lot less money getting the final design. So I think the right answer for almost every company is this mixture of where you have special knowledge and special expertise, you build something that is unique to yourself, your function, your desire, and then you buy IP to do the things that you're not a specialist in and other people can do much more effectively. And I think that's really important you understand that, because you're unlikely to have enough engineers to build everything yourself. And it's not wise to either. There's just no need to build something yourself. Just focus on what your expertise is, what your unique differentiation is. So how can startups get an SoC off the ground, and how can offers like Arm flexible access help with that challenge? Well, I think first of all, building an SoC it is not, I'm going to say, super complicated, but of course there's a lot of work to be done. And first of all, you need to decide what you're going to build yourself and what you don't need to build yourself. So, okay, which pieces of IP am I going to use to supplement my special knowledge? And sometimes you're not sure which is the right piece of IP. So, for example, the CPU, how much performance do I need? What power consumption can I afford to have? And you're not sure. So in the early days, you'd like to experiment. You might choose one piece of IP, simulate it, do your calculation, decide whether that's right for your design, or maybe you swap and use a different CPU that gives more performance or is better for your particular function. So I think Arm flexible access is a great way of giving these early startup organizations the flexibility to try different options before they have to commit even to which IP they're going to use. And it's transformational, really, because going back 15, 20 years, a company would have to say, I'm going to use that piece of IP, do all of their calculations on an Excel spreadsheet and whatever tools they use, and they'd buy that IP, put it with theirs, build the whole device, tape it out, and then find out whether that was really what they needed. Whereas now you're able to do such a lot of work before you even commit to silicon. Being able to trial different options is great for a startup who may not even be sure which market is the right one for them to be targeting. So it allows them huge flexibility. They can build something, trial it, before they even need to commit to the next level of funding. So ARM licenses synthesizable RTL, which can be put onto FPGA as well as an SoC eventually. When can using an FPGA be a good design point? So bearing in mind FPGAs give you a fully flexible piece of hardware that allows you to, within minutes, put a new design, a new logic design onto the board again and again and again and test it. So that's the flexibility you have. The downside is that the FPGA isn't able to hold as much logic as you can if you're building a SoC. So you're trading off speed of trialing your function versus how much area and power consumption you get. So they're the fundamental trade-offs at a very high level. But ARM processors can be synthesized onto FPGAs. Now that is a really good thing to do very early in your design phase so that you're still testing the software and the functionality of your prototype engine. And at that point, you really want to be able to turn around very quickly, every hour, every few minutes almost, to see whether the software and hardware combined are performing the function you need. The downside is it's not quite the same performance as the real SoC, so there's some limitations. However, you can learn a lot doing that, and I think it's a really good vehicle for very early prototyping. There's other circumstances when you'll use FPGAs as well, and that is where you might build a board that has many, many FPGAs that combined together are able to take your whole design that you want to put on an SoC, a real piece of silicon, and you can prototype the whole design, not just a small part of it, and run a lot of software on it. So it's again for verification, and we use that ARM uses that a lot to verify CPUs even. And there's a third situation where FPGAs are entirely appropriate, and that's where you have an application where there's very, very low volume and there's very proprietary hardware that you may need to tweak on a regular basis. So for example, and there's many examples out there I'm sure, if you were building a piece of functionality for high frequency trading that the finance people do in London, some of the algorithms they're building and putting into FPGAs combined with software. So these are able to connect to a network and do high frequency trading much more quickly than software can on a server. Very low volume relatively, very proprietary algorithms, perfect example for using an FPGA. So that FPGAs are a fantastic resource and can be used in these multiple different ways. Performance, silicon area, and power are critical components of an SoC. And how can you be sure you've got that balance right so that your eventual device is something that will sell in the market. It's got the performance you need, and you can sell it for the right price, and it's profitable. I mean, this is one of the challenges for a silicon design. It's always been the key trade-off that people would like to get right up front before they commit to silicon. And there's many different techniques you can use, one of which is basically rely on the information you already have from the silicon that's already available. So, for example, if there's a processor that's already in use in silicon, you have a fairly good idea of its performance, its power consumption, how much area that takes. And so, good, I've got a starting point. That piece of IP I can reuse, and I know what I'm going to get. And then you combine that with other techniques, some of which boils down to Excel spreadsheets. Again, I've used many of those in my time, where you're making educated guesses about the performance you can achieve with certain architectures, how much silicon area that would take, and how much power consumption you would get. And then you can do some early experiments of synthesizing blocks to see what the timing is, what the power consumption could be. And you have to build up all of these little elements to give yourself confidence that your design in total will meet your needs of PPA, power, performance, and area. And it's not an exact science, but there's many tools out there to help you get an answer before you commit to silicon, the EDA tools. And it's also important to consider the system around your SoC as well. If you optimize in a different way, you may be able to get overall lower power consumption and cost by building your SoC in a way that is slightly less optimized in one respect, but the overall system is better because of it. And these are the kind of difficult challenges engineers will think through up front in order to come up with good answers. But at the end of the day, using IP that's been used before by other people, by yourself, is a great way of having confidence of a large chunk of your SoC. Already I know how big that's going to be, how much power consumption these are going to be. And it's combining these together that allows you to have confidence in a solution before you get to silicon. So why is it important to develop software using fast models early in the development, and what are the risks if you don't do that early enough? Well, I think first of all, fast models allow you to run a large amount of software in a prototype of your system very quickly and very easily. Obviously, it's not as fast as real silicon, but you can develop a lot of new software, proving the interfaces between the different elements of the software interface together correctly, and you're able to make a lot of progress early in the software development. If you skip that step, then you're reliant on the full piece of silicon before you can develop that software. And often the amount of money that's been invested in building that piece of silicon is so large that nobody wants to find out that the software can't work because you've forgotten to put a significant piece of hardware in after the event. And then for another reason, is that the total software development can be a critical path after you've built the silicon to being able to release the product. And you don't want to be building all of your software from 0 point, only when you've got your silicon. You want to develop as much as possible before you have the silicon, and then you're just refining and adapting and doing the final verification before you release your full product. So it's a matter of getting ahead as far as you can. As I mentioned earlier, there can be 10 times as many software engineers as hardware engineers on some of these projects. So it's absolutely critical to get your software development enabled way before silicon is available. So a question about optimization of an SoC. You can tune different parts of an SoC for higher performance, or for higher power efficiency, or for the ultimate low power. And these are trade-offs that engineers need to look at and decide how to make. For example, you can choose to use a bigger processor with more memory on it to give you the highest possible performance. However, you'll end up with more area, silicon area taken, and more power consumption if you do that. On the other hand, your software will take less time to execute. So you have a trade-off, a classic trade-off that you need to think about. And these are difficult areas that you need to look in to really carefully and think, what is my total power budget? At any given time, you may have a limit on the power consumption of your piece of silicon. You don't want to overheat the chip, for example. You almost certainly have a limit on how much silicon area you can use. And so you want to be deciding which are the pieces that need high performance, even if it's only occasionally, on which are the areas that need to function, but the ultimate performance isn't really the issue. It's more how small the area they are or how low power consumption they are. And you need to look at the whole system design. And back a long time ago, they used to talk about something called Amdahl's law, which says that a system design is limited by the slowest element, or it could be the system is limited by the highest power consumption element. You need to look for which elements are slowing you down when it matters and decide to target only those areas to speed up performance. So you might, for example, say, let's build this with low area and low power in mind, and only build faster, higher performance where we absolutely need to. And that is one technique you can choose for keeping the power consumption down, keeping the area down, but making sure you don't limit the performance unnecessarily. And these are difficult trade-offs, and it's the kind of thing that is engineers enjoy doing, making difficult decisions, doing the analysis, trying to find out where the bottlenecks are, and deciding where to place their effort to increase performance. So what do engineers do when there are production issues, that some chips are failing after production, and how can we manage that up front to minimize that happening? This is a tricky area. You might call it design for yield. It's one way of talking about it. The first thing is you have to, when you tape out a chip, provide the ability to test the functionality of the chip as quickly and effectively as possible on the production line. So a chip is manufactured, they connect to the pads of that device, and then you need to be able to run a set of tests, inputs, and test the outputs to check whether it's functioning as you want it to. If you've got 9 billion transistors, you can imagine that's quite challenging, but there are techniques that have been developed over the years. And those techniques have become successively more refined. So, for example, when I was designing my first chip, we used what was called a self-test methodology, because it was for a military application where basically you effectively pressed a button and the chip went through a series of tests internally, which ended up with a checksum. And if that checksum was what you was expecting, you would say, we think the chip is working or not. Things have got a little bit more developed since then. And we then moved on to things like, can we run a set of patterns that proves every single wire in the design is not stuck at 0 or stuck at 1 because there's some fault in manufacturing, and then we developed tests to check whether that was so. And then you discover over the years there's more interactions that can happen where there's leakage between areas of the chip, or there's intermittency caused by a voltage spike in one area. Keeping it simple, over the years, many new techniques have been introduced, all of which are aimed at being able to prove whether a chip is manufactured correctly or not. And when you do that, you still find some chips don't operate even after running all these tests. You think it's okay and it turns out not to be, or you're having difficulty manufacturing because of the extremely small dimensions of these chips. And that's where new techniques have come in to analyze areas where there might be a high density of transistors or a high density of wires that are known to cause manufacturing issues, and you might target extra tests in those areas to show whether they're working. And this is a whole area in itself, and you have specialist engineers who become very familiar with the techniques needed and the way in which you use tools to produce tests and the way in which you analyze the devices. As an SoC designer, you're aware of these issues. You need to talk to those engineers. You may need to become familiar with some of the basics, but there's going to be a very large team. On the 9 billion transistor device, there's a huge range of different engineers with different knowledge bases and different expertise. And one engineer isn't going to have to know everything about all of these issues, but you need to know the person who does know, and you need to do what you can to help them do their job. A long way round of saying getting started on SoC design, you only need to worry about a few things as long as you know a person who knows the other things.